Now let's talk about how archaeologists date different objects. There are 4 common dating techniques within archaeology that we're going to talk about in this lecture. But before we get started, some important things to remember are that we can date a great many things, different types of things. We can't always use the same methods to date every object type or material type. And lastly, we do not need to date every single thing we find. So it's better and more economical, because some of these dating techniques are quite expensive, to target specific samples. Let's start with historical dating. And so these are methods that, deal with specific events or artifacts that have a known historical date. In this case, dates in historical archaeology tend to either define a temporal cutoff, or they estimate a central temporal tendency. So in the first case, there's what we call terminus post quem, which is Latin for limit after which. And this is the date after which the object must have found its way into the ground. In this case, there typically are manufacturer stamps on glass bottles or ceramics that can provide date ranges for us to make our estimations. Or let's say you found a penny in the ground and it has the date of 1804 on it. Well, you know that it would have had to have been made in 1804, meaning it could not have entered the ground in 1803. So whatever deposit that's in has to post-date 1804. In the other case, you have maybe some what are called mean ceramic dates, and this methodology tends to emphasize, a mid-range or median age over which, over the specific beginning and end dates of different pottery types. And so that can help you to account for, any kind of heirlooms or passing things down over time before they would have actually entered into the archaeological record. That brings us to relative dating. And what that refers to is the chronological relation of material with each other. These are indirect dating methods by which we are dating materials through their context or association, if you remember that from one of our past lectures. In this case, these methods cannot tell us when an event occurred, only the order in which the events occurred. So for example, layer X is younger than layer Y. The first of those then would be stratigraphy, and that brings us back to the law of superposition. It states that objects at the bottom of a stratigraphic deposit occurred earlier than objects above them. Well, archaeological strata do not always behave. They don't always follow that sort of geological strata or processes. So the example we're seeing here is a sequence of cave deposits, so sloping deposits downhill, that are causing some issues. So the sloping deposits, if they were then excavated straight down in an excavation unit, well, let's say you found a carbon sample and a corn sample from the same archaeological levels. These are arbitrary levels at which you would excavate. Well, you get some weird dates. How is it you're getting dates that are this far apart from the same layer? Well, when you actually pay attention to the stratigraphy then, which you would have found in your profile of the excavation unit, you can see, these are sloping. I'm guessing that potentially the corn belongs to a later layer, and your dates tend to corroborate that interpretation. Seriation is another relative technique, and it involves ordering artifacts in a sequence that correlates with an understanding of change over time. So we know styles and technological advancements can be seen in different material types. So if we look at Apple computers, for example, we see some big changes over time, and that is expressed in the style of the artifacts themselves. So if we organize our artifacts with like goes with like, so similar looking things together, based on that principle that styles change slowly over time, we can begin to understand patterns in the information that we're seeing. So in these cases, what we're seeing are different contexts, potentially whole units, or more likely stratigraphic levels within different units at different sites. You see these are the frequencies of different ceramic types then. maybe the shape of them, or it might be the actual decorative style of them. But what this is showing us is that this Vincent series was an early style that people liked. There was a lot of that pottery type around. As this one tended to go out of style, this Clements series came in and became much more popular, and at the very end of our sequence we're seeing that Gaston series is the most popular and therefore the most prevalent within the site. These are what we refer to as battleship curves or Ford diagrams. So let's take another more modern day example and look at the seriation of basketball uniforms over time. So what we'd want to do is take a look at the known trends of, let's say, basketball short length for players. Early on, they're quite short. We see in the middle of this sequence, they're very long, almost below the knee. And then nowadays, kind of making their way back up, I guess. Well, if we know we have these types of styles that we can place our data in, what we're able to see then is these changing trends over time. So as the short shorts went out of style, we see the longer, baggier shorts coming in and then out of style, and now it's more these, mid-length sort of shorts that we're seeing nowadays. Hopefully that helps to make this a bit clearer. A famous example of this is amongst New England gravestones, and if you're interested in reading the original article, there's a link there. But basically, researchers were able to determine that based on the style on the top of different gravestones, you would know relatively what decade you were in, at least, based on the trends as you're seeing here in the battleship curves and the popularity of different styles over time. Another example of relative dating is architectural dating. And so what we're able to do is determine the sequence with which walls were built based on whether or not they are bonded. So on the left hand, you're seeing the stones themselves are interlaced to create a corner, or if they are what's called abutting. And so in that case, this wall extending here would have had to have been in place before the wall on the left, theoretically. We would need some more information on what else is going on around here to be sure. Taking a look at this then for a small Pueblo site, what you should be able to determine then is that this sequence of 4 rooms here in the back were the earliest construction. It's a nice little 4-room set of rooms. Perhaps dividing them later on, you see these are abutting walls, not a bonded wall as we're seeing here. Then perhaps they added on this sequence of 3 rooms here, this room, and then the darker shaded rooms were definitely added near the end of the site's occupation. What we can't tell for sure is how these 2 features are related to each other because they have no architectural relationship. All right, next up is absolute dating. And these are dating techniques that determine the age of a material in approximate calendar years. So these are direct dating methods of the object in question. It's no longer dating an entire layer and using the context of that information. These techniques tell us when an event occurred on an absolute timescale, usually using a calendrical system. So the first of these is dendrochronology. And in the module, I'm going to include some additional videos that you can watch to learn a bit more about some of these techniques, dendrochronology being one of them. But the basic principle is that tree ring growth varies trees grow every year. They add a new ring. Those ring lengths or widths, they vary with climate. What you're able to do then is if you have a wooden artifact, take a nice cross-section of it, you can count the annual rings, and potentially you're able to align them with other known sequences from the region you're working in. So the region is important, the type of tree is important when determining where your artifact lines up with the local sequence. What the dating then is giving you is, if you have the bark on the outside, you know for sure that is your outermost layer. then you know the age at which the tree was cut down. Any lab that's going to give you a date based on that requires a minimum of 20 rings in order to match it with the local sequence. What you're then trying to date, the target event itself, is the construction of a building or a feature, any kind of remodeling phase that would have occurred, or the abandonment of the site itself. Some of the issues with this technique then are trying to account for what's called the old wood problem, and this occurs anytime there's, you can't account necessarily for stockpiling of wood. Just because it was cut down in 1230, let's say, doesn't mean it entered into the site construction immediately. Perhaps it wasn't actually used until 10 years later for construction. These are the sort of questions you have to be considering when evaluating the dates that you get back. Radiocarbon dating, there will be a video on this one as well in the module. But basically, any sort of organisms, plants, animals, us, out in the atmosphere, we are constantly taking in carbon. And we're also taking in the isotopic, the radioactive isotope of carbon, which is C14. When a plant, animal, or us, when we die, we as organisms no longer take in that C14. And so thus begins this constant rate of decay that we call the half-life. So we know that any organism with C14 in it, it's going to take 5,730 years for half of the C14 in that organism to decay and go back to regular carbon. So we're able to, say, have an animal bone, we can measure the proportion of C12 to C14 within that sample, and that's going to give us a date estimate for when that organism died. Now, all of these dates are given different statistical ranges, so you will see them presented as a plus or minus some range of years, and then you have to then go ahead and calibrate those into real calendrical years. Potassium argon dating, it's another radiometric method that's particularly targeted for old sites. So instead of the decay of C14 over time, we're seeing argon actually accumulating in a rock layer from the decay of potassium. Now the half-life in this case is 1,250 million years, not thousands of years, so we're talking some really old sites here. And what the technique is doing is actually measuring the time since that rock lithified. So since it went from a sediment into an actual piece of rock. These dates are available then for anything 100,000 years old or older. The precision, however, is about only 1 million years. So the accuracy of that is useful, but not for anything really recent. Archaeomagnetism. This is dating that involves looking at anytime a feature is heated up, if there's any kind of iron-rich sediments within it, let's say a hearth, for example, all of the iron-rich minerals are going to align towards wherever magnetic north is at that point. So if you're looking to date the last time that a hearth feature was used, you would take a sample from a part of the clay lining, let's say. You mark wherever true north, magnetic north is now. Well, there are known maps out there that then you can tie that information into. So they'll take it back to the lab based on where magnetic north is now, look at how the iron-rich minerals are aligned, and give you your date based on the known trajectory of north over time. Obsidian hydration is another type of dating that goes off the principle that once a piece of obsidian enters into the ground, it begins to absorb water from its environment at a constant rate. And this forms what's called the hydration rim. And so that's actually this area here between the two arrows in this photo on the bottom right. Now, the rate at which water is absorbed depends on the source of obsidian to begin with, the soil moisture in that area, and temperature of the environment. Measuring the thickness of the hydration rim then can provide you with the age that you need. It'll be in years BP with some sort of standard error range. Now, this is a cheaper method than radiocarbon, but you need to keep in mind that the date you're getting is the breakage of the obsidian, not when people stopped using it. So depending on the use life of the obsidian artifact, I mean, we're still talking within a couple years probably, so it's pretty good. All right, last but not least, there are what's called trapped charge dating techniques. And these rely on the fact that electrons become trapped within the crystal lattice of different minerals as a function of just the ongoing background radiation that we experience here on Earth. These techniques can date objects beyond the range of radiocarbon, so at least 300,000 years or older. So the principle behind these techniques are that radiation is trapped in the electrons at a constant rate. So the age of a specimen is total radiation that they've received, doubled any kind of annual dose of, divided by the annual dose rate of radiation. How you determine the annual dose then is you need to install a dosimeter. You bury it within your archaeological site for a year. It helps you to then measure how much radiation the site experiences within any given year. And then that helps you to determine the age dating of your samples. The sorts of samples that you can use these techniques on, thermoluminescence is used to date the last time any object was heated. So pottery is a good example of that, whenever it was fired or last used to prepare some sort of meal. There's optically stimulated luminescence, or OSL, and that actually is measuring the the last time that sediments were exposed to light. So I've seen this used in canal features, for example, the last time the sediments were exposed to light and then became buried by mud and other deposits coming through by water. And lastly, there's electron spin resonance, which helps to date tooth enamel, which does not trap the sort of charges when it's formed.